Hi everyone, this is just a quick little video about a technique for determining activity coefficients in a lot quicker fashion than using that big formula that was from the Debye-Huckel formula theory. Um, so this is called interpolation, and it's from chapters 7.2 in your textbook. It should speed things up, and this technique can actually be expanded to things beyond just activity coefficients. You can actually do this for other things with linear relationships, but it's actually really useful for activity coefficients. So again, this is from 7.2 in your textbook. And so what we see here is the concept of interpolation is that basically if you have two knowns here, in this case that both have an x and a y dimension, in this case, for this example here, this is your known, and this is your red pen, that will work a little better. Right, so this is a known piece and a known piece here, and both of these have a known y value associated with them. Right, you may want to know an unknown y value, right, and you may know that x value. Okay, so this is just really generic terms, but this can be applied to activity coefficients. So the idea is that the unknown y interval, if you're assuming this is a linear, so that's key, right? Where the assumption is that this is a linear relationship. Okay. So this has to be linear for this to work out, because this comes out of basically assuming that your slope of your line is the same. And then if we know an x interval, but we don't know a y interval, we can solve that using a known y interval and a known x interval. And the other key that you want to make sure is that your unknown is sandwiched between two knowns. Alright, so we're going to run through a quick example here. And that would be what is the ionic strength of a solution of iron, or what's the activity, sorry, of iron 3 plus, ionic strength of 0.03 molar. So one way we could do this is to use that equation we showed you before where you solve for the log of your activity coefficient, but that can be pretty time consuming, particularly if you have to calculate a number of them. A shortcut you can do is to interpolate. And so how we do that is we go and we find two values. So remember, we are looking for ionic strength of 0.03, so we're looking somewhere between these two, excuse me. So somewhere between 0.01 and 0.03, okay? So we're looking at 0.03 molar activity. And what we're wanting to find is iron 3 plus. So we're looking down here, iron 3 plus. And so between 0.03 we have 0.445 and 0.245. So I'm going to set this up something like this. So what we're going to have is, let's get rid of that. What we have is an x and a y. And so what we do is we sandwich our x between our unknown between two x's that we do know. So we have 0.010 and then 0.050. And what we don't know is 0.030. Okay, and so we do know the y is associated with the other two. Right, we know that from our table, we know that at 0.01 ionic strength, molar ionic strength, our activity coefficient is 0.445, and at 0.05 our activity coefficient is 0.245. Alright, so we just use this equation here to solve for that. And so how we set that up is that we set up our difference between our known and our unknown. So I'm going to set this up. Our y is going to be on the left here, and we're going to have 0.445 minus, in this case this is our y, so I'm just going to use this blue so it stands out. So this is our unknown. So we're trying to solve, we're trying to solve this one right here. Okay, and but this is going to be equal to, all right, if the ratio of this over a known interval, which our known interval is going to be between 0.445 and 0.245, so we put that up here, 0.445 minus 0.245, but this equals, right, our value that's associated with this, our x value, which is 0.010, minus the x value associated with our unknown. In this case, I'll keep this in blue. So minus 0.030, and then we're going to do our known interval on the bottom. So that is minus 0.010 minus 0.050. All right, so if we go through and we solve this, you can just, it's a pretty simple arithmetic at this point. You can just solve for y. What you should hopefully find is that y equals 0.345, okay? And so, so what you should find is if you, so this y in this case, this is our gamma, okay? So gamma iron 3+. Right, so this is our known values here. These are our gammas. And these here are our ionic strengths. So this shows if you have two known activity coefficients, or gammas, and two known ionic strengths, then you can find one in between, because the relationship, particularly at close ranges, is fairly linear. So if you look at our activity coefficient, right, the one that we just calculated is 0.345, and hopefully that should fit right in between these two, and it does in fact fit right in between those two, so this is 0.345, which would be our activity coefficient at mu equals 0.030 molar. Okay, so that's just a little quick shortcut. Again, either way, if I ask you this question on a quiz or a homework assignment or exam, you can take either one of the methods, either this or using the Debye-Huckel method. This may be a little quicker for you, particularly if you're doing a number of these calculations in a row. So that's interpolating activity coefficients, and that is chapter 7.2 in your textbook.